Hello, ladies and gentlemen. This is Peter Bernhard from MESCO Engineering. And welcome to this webinar. Today, we are talking about a success story for an implementation of a safety robot cobot AMR. And we want to give you some insight about our development work, how we did it. So have fun. So today we are talking about the Safe Drive technology module development for the cobots. A few sentences before we begin with the content about MESCO Engineering. So we are a service company and we are doing hardware and software development for the branches of factory automation and process automation. Our main skills are industrial communication interfaces, functional safety, and explosion-proof designs. So next to our engineering services, we have also design packages which we use as a kind of a basis for our developments. These are kind of pre-developments. Yeah, we are doing engineering service, design service. So we begin with a customer relation, mostly with a workshop, and define the idea of the development, derive out of this some requirement specification, and then we enter in the stage of doing the hardware and the software design. After this, PCB design will be done to have a layout, a PCB, and then integration testing will follow and system testing to end up with a prototype, which will be given then to the customer to manufacture. So our slogan is where ideas turn into success. That means we start with the idea and we end up with a success for the customer. Yeah, for safety reasons, we are having some proven development processes. For example, we have an accreditation for functional safety management. This is yearly accredited by TÜV North. And for sure, we have also ISO 9000 certificate for the hardware and software development. So we do mostly safety critical systems and industrial communication stuff in product development for these process industry and factory automation industry. So today we are talking about the success story for a safe robot cobot AGV drive. So we are talking about the typical challenges which we had also in the development. Yeah, when we are looking at such a robot or cobot, so we see different applications which you can realize with that. So if you have a robot, for example, it's different as you work with a cobot in a collaborative way. For example, there you have some topics that you have to limit, for example, force or speed. And in automated guided vehicles, you have also the challenge, for example, to monitor your environment and to save, to guard people or environment. Mostly in this development topic, you have to support field bus systems because you will have a main CPU or a PLC, which is controlling the HMI or the robot. And this is done mostly with field bus system. If we are talking about a safety device, then we are talking about also safe field bus. If you have the requirement, for example, if you do a robot design, sometimes you will have the requirement that it needs to fit to a certain standard for the interface. And we will come later in this webinar for the SRCI interface. This is very new. It's a standardized protocol how to get different vendors from robots in one plant together. And you can handle it, parametration, diagnosis, all will be standardized. What you also need for such a development, if you do a safe drive for a robot, you need fast reaction times and mostly a very small electronic footprint. especially when we are talking, for example, about a drive which is controlling limbs of a robot or arms of a robot. And so you will have not much space. And so it's a very hard requirement to, yes, to stay in the space limitations and to develop a very small footprint electronics. Also very important are the safety functions itself. So there are different kind of functions. I will rely on this later on. Also stop functions, for example, but also monitoring functions to monitor speed control or speed limits or whatever. This is important to be sure that the robot works in a safe area and in a safe operation mode and does not hurt anybody or yes, yeah. What also is important is to fulfill the safety development process requirements. Mostly you have certain standards which are behind this development. Mostly the IEC 61508 is related, or you have other robot standards, for example, or AGV standards as the 3691. What we face in our developments is that the customer has some ideas about function set of a kind of a safe drive, which should be implemented for a robot, but not all functions have the same priority. And that's what we also report about, to have a smart go-to-market strategy, to do not all the things at once, so do it by steps in kind of launch waves. Okay, when we talk about the use cases for robot, cobot, AGV applications, so you will see there are some safe functions you see on the right side. The most standard function is safe torque off. Safe torque off is more or less to switch off the power to the motor, which then stays the motor in the safe control, and and then it stops. You have also the safe stop 1 and the operating stop and the safe stop 2. These are two stop modes which are time controlled or ramp controlled. And you have, for example, the safe direction where you say, okay, I go forward or I go backwards safely. You have a monitoring about the maximum speed. You have a limited speed monitor, and you have for example, safe speed monitor that you can monitor the actual speed of a drive, and you can do brake control or brake test. These are different applications. Here in that table, you see the safe stop and emergency stop you need mostly anyway. And if you have, for example, a safe brake and a safe parking position, then you need, for example, an operating stop or the stop categories SS1, SS2 to be sure that the vehicle, for example, is not moving while you are loading, for example. Then, for example, detection systems, there you have the topic for the safe direction. That means you detect a person, for example, which goes into your direction or leaves the environment, so you can handle that. And also the maximum speed to see how fast, for example, is a person detected, or better said, which is how fast it is approaching to the hazardous area. You have some speed supervision. This could be, for example, a safety limited speed. If you have, as an example, you have a pick and place robot, and there you have a safe speed limit. Otherwise, the weights are lost or the loads are lost, or people get hurt, simply said. And also safe load handling and stability supervision. There you need all kind of stop categories or safe functions. It's very depending on the application. So the goal is that you can rely on this safe function, and you can work together with a robot in a very collaborative way. and to be sure that it's not hurting you or any environmental stuff or the plant or whatever. And in the past, you have light curtains, and you almost shut down the robot. And today, with these functions, is it possible to directly interact with the robot, work together with the robot, and not simply said shutting it down? So you can work. It's slowing down, for example, if you go closer to the robot, and it continues if you leave the hazardous area. And that's why these functions are so important. You can, if you use it, or if you have a drive with such safe stop functions, yeah, you don't need so much laser scanners, light curtains, and so on to save your directly work environment. If we have a look at a block diagram for a drive as an example, so you have the blue block, the AGV communication and control block. This is, let me say, the most standard control block who is doing the speed control, the direction control, and controlling the motor. And you have also I/O interfaces and sensor and actor, which are non-safe. Blue means here in that diagram non-safe. And mostly in these cases, you already have any kind of field bus system like an EtherCAT or a Profinet connectivity. And for sure, you have the control signal for the motor driver, which controls the motor. That's the normal operation with non-safe. For a cobot or for a robot, which is safety relevant, you need more. That means you need, for example, a monitoring system, which is really monitoring the standard operation of the AGV communication and controller. That means this yellow block B here in that diagram is based on a redundant architecture, which has two microcontrollers, and they are interactively exchanging data and cross-monitoring. And they just monitor the normal function of the controller, of the non-safe controller. And if there's something happens which is out of control, out of limits, then the safe controller takes over and does the measure to, let me say, stop the system or to limit the speed and so on. So if you see the other light yellow blocks, for example, you have another block with a safe brake control. This is needed, for example, if you have a hanging load and you need to brake. Otherwise, if you stop, the load will go down and could be a hazardous area then also, because falling loads are critical. And to monitor, for example, the speed, you need to have a kind of a feedback where you have an encoder. And so you need to monitor also the encoder feedback, if it's in the range or out of the range. And then if you see, okay, it's in the range, you do nothing. If it's out of the range, then you can directly take over control. Also with the safe I/O, you have sensors and actors connected. For example, this could be light curtains, this could be bumpers, it's, switches, emergency shutdown devices which are directly connected. And so you see the yellow parts in this typical application will be added to the standard controller. And this makes it possible that you can use the standard controller with, mostly as an option card, realized you can use this to save the standard movement of the robot. To summarize it, we have on the left side A, we have the robot controller, communication interfaces, EtherCAT, Profinet, for example, any other Ethernet-driven field bus systems are also possible. You have a safe and a non-safe communication package, which comes in, for example, from a safe PLC. So block A receives the safe and non-safe communication data from field bus. And you have also, for example, in A, some custom-specific interfaces. And in B, you have the forwarding from the safe packages which are received by block A. And these safe packages are transferred to block B. And there you have that safe core architecture for the safe function. So these packages are unpacked here in that block B. And yeah, like I said, redundancy sign. And then you are also controlling the safe IO, which are in block C. Could be input, it could be an output, for example, to switch something, to hold a brake. You have some OSSD inputs, for example, if you have light curtains or laser scanner connected. Encoder interfaces, this could be Hall sensors, TTL, SYNCOS, or also encoder with encoder protocols, like, for example, Hyperface N.BIS. This can be connected there, and also safe custom-specific interfaces. This depends. But this is more or less the logical function of this architecture. And the other yellow parts are, like I said, safety relevant. And so you have a standard. It's IEC 61508. And this is okay for SIL 2 applications, but also for SIL 3. In most cases, we are doing developments which are also following the 13849. Mostly you have here CAT 3 performance level E, or also D. It depends from the application, whatever your robot needs to have. Due to the fact that these kind of developments are quite comprehensive, people think about doing it in waves. That means not doing all at the same time, but what is the most important function? This is mostly a standard STO, what means save torque off, switch off the motor. And you can do this, for example, with a save digital input as an emergency button, or you can do it a bit smarter with, for example, a save field bus. And then you can invoke the save function by a safety PLC, which says, okay, motor stop. And you transfer this data, for example, with a telegram like ProfiSave or EtherCAT FSOE. This could be, I would say this is the launch wave one. It's a minimum set of safety function. And what we see in the requirements from the customer, which are doing safety robots, is that the advanced stop functions like limited speed or safe direction is also very important. To realize this, you need a kind of a feedback, what means you need a kind of an encoder which is connected. It could be a safe encoder, it could be a non-safe, which you do, let me say, calculate the values out of a non-safe to do a safe value. This is possible. And so this could be a launch wave 2, for example, to implement advanced stopping function. It depends from customers, from requirements, if you do it all at once or do it in steps. And in some cases, we have also, as a further option, I would say, you have save IO. For example, to control a brake, or to simply say on off for important devices like pumps, ventilator, heating systems, and so on, or simply also to have a safety input to react on other devices which have safe output. So you can have a kind of a safety circuitry which reacts with logic to inputs and output. And if you have one field bus system and you go to the market, you will be requested soon for another field bus system to cover all the world's field bus systems. So you need another one. So in that example, for example, you're going to start with a ProfiSafe, and then you could also add further either CAT FSOE or vice versa. And also the same with the encoder. Sometimes you start with the connectivity of one encoder, and if you ask your customer, mostly they answer, I will have the other. So you need also to support different encoders which will be connected to a drive. So what we see in the development is that really some customers do it all by one, but also others do it in steps, like here shown as launch waves. Okay, so how do we do such a kind of a development? We start mostly the development with a technical workshop to clear the high-level requirements for the safe drive development. So these things needs to be clear before we enter in the development, but better said, the system design requirements spec and the safety concept. This procedure is a bit driven by the standards for the IEC 61508. We at MESCO, we do mostly a concept approval. That means we do the architecture and the safety concept, and then we get an approval by the TÜV for the implementation. And this works very well because then the TÜV is already informed about what you plan to do. Then there will be a technical prototype implementation where all the functions are implemented, but not tested safely. What means we've learned that this is a smart idea to do all the functions properly in a, let me say, non-safe way, but using safety parts out of this. Because if you have any changes, if you have any deviations or wishes, you can implement it smart and not having the burden of all the documentation which comes along with that. And after that, we do the functional safety proto 1, which means we implement this, performing all the hardware, software tests, doing all the documentation which are necessary, for example, for submission to TÜV or any other notified body. And also, this safety prototype will go into production, for example, at the customer site. And if there are any deviations, changes, this will then influence the implementation of the safety prototype too. Normally, we are calculating one redesign for a prototype 2, because normally you will have any issues which needs to be fixed, and therefore we see that in most cases a proto 2 is necessary, even to correct the bugs or to fix any deviations from TÜV, which comes as a hint or as a revision from your documentation. At the end, there will be a certification. Normally, we support also this certification with the customer together at TÜV, because when we are the author of the idea, we had the idea for the implementation, we can also directly answer these questions from TÜV. And this is also in a very close collaboration with the customer. What we need to do is that we have to follow, because it's a safety development, we have to follow a strict process. So we implemented at MESCO the V model as a development process, and this model is certified by TÜV. The implementation for this certified by TÜV every year. So simply said, it starts with a kind of a spec. We draw up the system requirements and architecture. And with that, also the safety concept is included, which will be approved by TÜV. And then we go in the direction of hardware requirements, software requirements, design, hardware design, software design. In the hardware path, the layout will follow. In software path, the coding is following. So we do the software implementation. And if this is in place, there will be a system integration where the software comes to hardware. And then we begin with the hardware module tests, the software module tests, integration testing, and then it comes to system verification, where also customer is on board, and then we do the validation testing at the end. And this is followed by functional safety assessment, V&V planning, change management planning, and also we are using also software packages which could be reused or are proven. And so we will follow that path completely. For the robot implementation, sometimes you have the requirement to implement a standard robot command interface. This is quite new. More or less, this is a generic interface to support different robot controllers to one single PLC. This is a very new implementation or a new specification which could be implemented by robot controllers. If you have different vendors, normally you have different tooling to program the robot. And with this interface, you can do the generalization of the robot interface, for example, and you spare a lot of programming because you have one single application and you can add several robots to this implementation. It is the SRCI interface is already implemented with Siemens. You can use it with the TIA portal and Profinet for this robot integration. And you have the nice thing is you have a generic set of standard robot functions. And this is more or less vendor independent. So you can use this as a kind of a library if it's implemented in the robot as a subset of commands. And then you can directly use and diagnose the robot as it would be from one vendor. So if you do a robot development, you need to think about the implementation of this SRCI topic. There is also a test suite available from Siemens to grant the implementation of this interface. We did it once for a robot client, and it was also certified with the conformance tests. And just to mention, MESCO is certified Profinet competent, or we do a lot of Profinet implementations also for customer, not only in SRCI, but also on drives and also on other products. Okay, we want to show you now how we gonna develop such a kind of an option board for a drive. I come back on this diagram, which we already have, and I just want to tell you some things. For example, the stop functions are important. We learned about this, what they mean. And for example, if you have only the safe torque off function, so you're going to need more or less the safety core, and you have to have the torque off signal, which is going directly to the IGBTs and switch off the motor lines. That's mostly hardware-wise a quite straightforward implementation, and sometimes you can directly insert this circuitry on your standard controller. And for the more advanced functions, then you can use for example, the redundant structure of the CPUs and also the encoder interface and I/O just as an option card. So we see often that we implement the STO on a standard controller board for the motion controller, and then let me say the advanced are separate in an option board. So you see here, for example, the safe torque off goes directly to the IGBTs. The safe brake control goes for sure to the brake because it needs to brake if you have hanging loads. Encoder interface has a connectivity directly to the redundant safety board, and also these I/O stuff goes directly to the redundant CPU board. Okay, we implement such a safety product by using some design packages which are developed by us. For years, we did developments in functional safety, and we derived out of this some design packages which we could use for the safety architecture for different applications, not only for robots and for cobots and AMRs, but also for other safety devices. And the design packages consist of functional blocks. We have templates for requirement and architectures, especially, for example, these redundant blocks from CPUs. We have several software libraries which are used here for this implementation. We have hardware which is proven. We have schematic artifacts. We have test artifacts to do the testing for different functions. And also we have templates beginning from the phase 1 document for the safety requirements specs, safety concepts, up down to the level of test documentations. To give you an overview how that looks like, it's a platform which we use as a kind of a prototyping platform, I would say. It's a base plate with power supply. You can connect several modules on it. Could be Ethernet interfaces, and it's a redundant microcontroller and I/O block. And when we do such a development, sometimes we start with that platform. That means we are using evaluation boards which are in place. Do then the custom specific design work and implement the software packages on it. They are following the requirement specification which come from customer. And then we do a kind of a first prototyping to, for example, to write also the GSDML files or AC files for the field bus systems, that the customer see how the device will look like at the PLC site later on. And then the hardware development runs in parallel to these topics. And if the hardware is in place and the hardware comes back from manufacturing, we take over this software which was written to the target hardware and to the system integration then, and hardware software integration on the target platform. So this is mostly used as a starting point if we have no hardware available. If the target hardware for the safety drive is available, then we go to the right platform. Just a few words about this evaluation boards and our platform. It's based on the STM32. We use here a type of F7. And on these two micro, they have I/O monitoring, handling, implement software libraries for the drive functions. We have also implemented deep coupling measures. They do cross communication, and they have address switches for the field bus addressing, debug interfaces, and also some diagnostic measures like temperature sensors. And for this, for example, we have templates for the design documentation. And so it's quite easy to have a customization of this to run then the software and hardware on the customer's target. And if you look in detail, the safety architecture look like this. It's totally redundant system. You have power supply, you have MCU, which are cross-communicating. You have safe input handling, safe output handling. And also the communication is on the principle of a black channel. That means safe, non-safe data are on the same line. And the safe data are forwarded to these two MCU, unpack the data, and then you do more or less a comparison of the data. And then if it's okay, then you switch output or whatever. This is the basic architecture. In software, we have a bunch of libraries which are, let me say, non-custom specific. These are used in many projects. For example, we have the 1/2 base, what means these routines are running on the CPUs. This is, for example, a scheduling. So we don't need a real-time operating system, which is mostly expensive and has license topics. So we are taking a scheduler. It's a very clear, transparent task handler, more or less, to handle the safety tasks. We have a cross-communication lib. We have self-test lib for the memory, device diagnostics. We do failure handling if something happens, so we will detect it. We take care about parameter storage, also for example, the firmware update, non-volatile memory handler, service com. This is the interface which goes mostly to the drive directly, to the non-safe part. If you remember, this was block A, which I introduced it. And this is the interface from drive to the safety part. And this is secured and has the protocol inside to grant the transmission. We have some debug interfaces. We have All the software is written in that way that we have a hull to port the software easily to other micros. And we have, especially for this drive functions, we have some libraries which cover the safe function for drives, like, for example, the safe speed, safe stop, safe acceleration, brake, and so on. This is all covered in a library. And also, we need mostly some field bus interfaces. So we have also a stack implementation for ProfiSafe, FSOE, and we take care about the software updating and the parameter download. So it depends if you have a tool or if the parameter download goes via the field bus system. That depends. But these are all core functions which are in place, and so we can use them or customize them. Yes, and out of this, we built up the Safe Drive Monitor. The Safe Drive Monitor is more or less a set or a subset of different functions. These are hardware-related tasks where we also have evaluation boards to start up with the hardware. And so you see here connectivity, for example, to Safe PLC, bumper, Safe laser scanner. Then we have that abstract layer, and then we go more or less to that safety software libraries and the ecosystem. And these portions are, these artifacts are written according to the standards of 61508. Also with the documentation artifacts and the testing artifacts which are in place. And if we do a customization, this is all based on this, and we can reuse it, adapt it, customize it, and then preparing a proper documentation which we give then for the certification from TÜV. And with this basic set, we can use it for different applications. It could be for a robot, like I say, or for a cobot. It's more or less no different. Also for an AGV, an automatic guided vehicle, is also the same core. And with this subset, we implemented the drive, for example, for this robot limb. Yeah, it's like I said, it's based on a 1 out of 2 system. We have 61508 design. It's feasible to use it for a cell 3 implementation or for CAT3 PLD use case. We have libraries for different applications. We have advanced safe drive monitoring library, which is covering the speed monitoring and the encoder master and feedback functions for the encoder. Also, the I/O handling is there. That means with digital input, digital output, brake control, or safe torque-off functions. And also the Ethernet connectivity with the field bus system. Though this is a living platform, which means if other field bus systems comes up, then we will add these functions to this platform to realize efficiently safety developments in that area. So thank you for watching. And if you have any questions or if you have a request for the development, or if you need any consultancy, or if you are very clear and have already a requirement specification in place, you can send it to us, and then we can have a chat about the possibilities how to implement such a safety device for you. And at the end, you own all that development results and can build out of this a platform for success. Thanks for watching. Bye-bye.